Okay, welcome back. So, in the previous class we have proved the mean value property, that if U satisfies harmonicity, then it satisfies the average of the every value can be obtained by looking at the average, either as a surface average or a volume average. Then we have stated a theorem, the converse is also true. That means if U is a C2 function and satisfies the mean value property, then U is harmonic. And I made some final remarks that the C2ness is not really needed, but the proof is different. If you assume proof that U is C2, the proof is quite easy, which I am going to do now. So, let me recall the once more theorem stated earlier. So, U belongs to C2 omega satisfies U of x is a U of x or U of y, whatever it is, does not matter. So, U of x equal to 1 over boundary of B, integral of boundary of B, U I interchanged the variable, does not matter. That is the same as 1 over B integral over B U of y dy. And this is for all, you take any point here, you take any ball, does not matter, any ball B here, okay, whatever be the radius. Okay. For this should happen for all B compactly contained in omega, that is important. Okay. Then Laplacian of U equal to 0, that is the conclusion. So, let me give a proof. Proof is quite good, easy, not very difficult at all. So, you look at the balls of radius r. So, look at ball of radius r centered at x, that is what we will do it. Okay. Look at here and then define HR is equal to, define a function HR is equal to the ball of radius r. So, you have your HR modulus of d Br of x, any ball, okay, Br of x. Br of x is compactly contained in omega, integral dBr into U ds. And this RHS, so this is true for all Br, right, Br contained in omega. That means this is independent of the ball. So, you are defining x. So, this is the same value that is given to be Ux. That means this implies HR is constant. HR is a constant function in a neighborhood. Okay, that is all we had. Constant in a neighborhood of R 0, that is it. So, constant function when R is big, the ball will go far away, but we are only bothered about the neighborhood of R. So, that implies the derivative of h prime of R equal to 0, right. So, since h is a constant function, now we compute HR in a different way. So, let us try to compute HR, h prime of R. So, you have HR, so recall your HR once again. So, let me not write. So, you differentiate. When you differentiate here, as I said, the integral is with respect to R, there is a variable here. These are all depends on R now. So, you cannot take the differentiation immediately inside. What you do is that you again make a change of variable of translation and a dilation. When you make a translation and dilation, you can write HR to be the same way. You can write it will take care of the parameter correctly. It is the same as all these parameters will come correctly. We have done it some now 1 or 2 or 3 occasions. So, we will not repeatedly do again, but we will be using it again and again. B1 of 0 Okay. So, you make this translation u of now x is the point. So, you use x here plus some tau z. Okay, so let me not get confused with you some variable does not matter. So, h r. So, it has to be r z ds any variable you can use it. So, I am making a change of variable here. Okay. So, with change of variable this will be this one, this is on the boundary. Okay. Now, I can differentiate. So, therefore, h prime of r is equal to, now it is all independent of r, d b1 of 0 integral of b d b1 of 0. Now, it is a multivariable function. So, you know how to differentiate with respect to this variable r. So, first differentiate with respect to all the variables xi, that will produce you grade x, and then differentiate with respect to r, that z is a vector now because it is in the ball. So, grade u dot z is equal to ds of z. Okay. So, you get that. Now, come back to the original thing. If you come back again, make a dilation and translation in the other direction, this will become b r of x. Again at the point you get b r of x integral of, I am repeatedly using the same thing which you have that thing. Now, you will have grade u back to y. So, your change of variable in this direction is y is equal to x plus r z. So, from here you are again going back. So, you are doing the same variable. Now, you are so this is x here. So, you have the thing the other way you do this one same thing. So, your z will be y minus, that is your thing, y minus x by r ds of y. You see x is fixed. So, it is a change between y and thing. So, here y minus x by r, that is your change of variable. Okay. And but what is this? This is nothing but your normal. This component, this is your normal. Once that is normal, your this one, so this one is your normal derivative du by dr, and normal is du by dr. So, you can write this du by dr. So, you have this equal to 1 by modulus of dbr integral of dbr du by dr. Now, apply your divergence theorem, divergence theorem, divergence theorem. Okay. Once you apply your divergence theorem, this will be 1 by modulus of dbr integral of Laplacian du by of y dy over your br. So, what did you get now? So, let us, and this is 0. So, you already know this is 0, prime of r. So, that implies integral of Laplacian of u of y dy for a ball of radius r around x is equal to 0. Now, that gives you a contradiction, because this is a contradiction. Why this is a contradiction? If Laplacian of u of at y some point y naught is positive, by continuity will imply Laplacian of u of y will be positive in a neighborhood of y naught. That will imply integral of Laplacian of u of y be some neighborhood for some r, this will become positive. So, this is, that is a reason it is a contradiction. So, you have your result that the converse to the mean value property. So, we have, and this mean value property is extremely useful in the proof of many things, and you can derive many results. Okay. As we go along, we may see some of them. Now, with this, let me go to another important thing, what we call it maximum principles. Maximum, another important thing, maximum and minimum principles. This is basically a trademark of second order differential, trademark of second order, though you may be able to prove some results for higher order, second order PDEs. Why this I say that it is a trademark? So, let us look at an example, one dimension case, example, one dimensional case. Suppose you have a function f defined in an interval AB and to R, suppose is C2, that means twice f. So, you have an interval here, and suppose f prime, look at a function something like that. What can you tell about this point? So, this is your AB and this is your point C. This is maximum point. At C, you know that f prime of C equal to 0, but f prime of C can be 0 even in the minimum point, and at the maximum point you get f double prime of C is negative. So, what does this conclusion tells you? If f double prime of C is positive in a neighborhood of C, then C cannot be a maximum. C cannot be a maximum. This is one of the motivation which you get it. So, whenever you continue, whenever you find that f double prime of C is positive in some certain region in the neighborhood of C, then you can say that function cannot have maximum there at that point. So, in the general elliptic operators, this f double prime, that is what I said, it is a trademark of second order. This replaces by second order operators. So, what kind of operators you can derive such maximum principles? So, what you will see in this class, not about general elliptic operators, we will derive such maximum principles soon for the Laplacian operator. So, the Laplacian replaces the second derivative or other elliptic operators. So, you can refer other books like in other than our book, you can also get into other PDE books like Gilbert and Schrödinger to see various maximum principles in the context of second order, context of maximum principle. So, we want to derive. This also has a sometimes this can use, you can derive comparison theorems. Derive comparison theorems. So, certain operator, certain theorem, say suppose you have an equation of this form, this is a nonlinear operator, nonlinear, and you can compare results, compare the solutions between these two if Laplacian equal to such that suppose you know that u equal to v on the boundary of a domain. Suppose you know that this is in omega, so you know that one. And then if you subtract it, you get surplus n of u minus v is equal to u square. It is, you will get it as a, this you immediately see that this is a subharmonic, which we are going to derive now equation, and u minus v equal to 0. So, you will be able to compare solutions between a problem which may be little difficult, but then other problem will be easy. You will be able to do some comparison results. So, our aim is to derive maximum principles for the operator Laplacian, but you can have more general operator, okay, which we will not be doing it here. Maybe I will give an example if I have enough time. Okay. So, let us to derive a strong maximum principle. The proof is not difficult, but the result is very, very important, and you also see an application of the maximum mean value theorem, strong maximum principle. It is called SMP. We may refer it that way, SMP. Okay. Assume omega is a bounded region. That means open connected. Otherwise, you can apply to each connected component. And u is a bounded subharmonic function. Okay. Then okay, and okay, if there exists a point y in omega such that u of y is equal to the maximum of u or supremum. So, let me even write a supremum of u in a omega, then the conclusion is then u is a constant function. It's a constant function. You see, that means, that is in a sense what it says, that a non-constant function cannot have an interior maximum, cannot have an interior maximum. Try to understand the theorem very clearly. That means, if you have an interior point, that means you have a domain like this, and if you have your y and the maximum is attained or the supremum is attained in an interior point, then that function has to be a constant. A non-constant function cannot have an interior maximum for a bounded subharmonic function. So, if u is superharmonic, the other way result. If u is superharmonic, okay, a non-constant then you cannot have an interior minimum, cannot have an interior minimum. And the third result, a non-constant harmonic function cannot have interior maximum and minimum. Interior maximum and minimum. Okay. So it's enough to prove the first part. Okay. Because once you prove it for a super subharmonic function that, and it's a non-constant subharmonic function, cannot have an interior maximum. For a, if u is superharmonic, you apply the same result for minus u. So minus u cannot have an interior maximum. That means you cannot have an interior minimum. And if it is a non-constant harmonic function, you apply the results for both u and v. So it cannot have either a maximum or a minimum. So let me try to give a proof based on a topological proof, basically. Topological proof. So let m is equal to supremum of omega, supremum over omega of u, and that is given to be uy for some y. There may be many y in omega. So you define omega m is equal, you collect all the points, set of all points y in omega such that u of y, set of all points x, y is a given point, set of all points x in omega such that u of x is equal to m, which is non-empty by the given assumption, equal to empty by assumption, right, assumption. So we will prove that we prove omega m is both open and closed and open, closed and open. So once you prove this, this will imply if it is both closed and open and it is non-empty, omega m is equal to m omega itself, because if it is both closed and open, either it has to be empty or it has to be full domain omega, and that is implies ux equal to m for all x in omega. That is it. So it proved it's the thing. Omega m is closed is EC, so we will prove first that closed is EC. So you choose xn in omega n, xn in omega n, omega m, and xn converges to x. But then u is continuous. Okay, since u is continuous, what do you get it? Xn is in omega m, so that m is equal to uxn, and by continuity uxn converges to u of x. That implies u of x is equal to m. That is x, that implies x is in omega m. So omega m is closed. That is a trivial result by the continuity of u. So this is something like a kind of surface, right? Immediately you see that. So let us prove omega m is open. That is a bit more involved, and you have to prove this omega. So you have a point, so you want to take a point. So what do you want to prove it? You have to take a point z in omega m. Okay, you take a point. So you do not know omega m, so just suppose this is your omega m. This is not omega, be careful. So omega m will not be open, you want to prove it. You want to choose a point here, you want to choose that there is a neighborhood. You want to prove there exists R positive such that BR of Z is in omega m. Okay, you have to prove that. That is, you have to prove for all x in BR of x, Z implies u of x equal to m. So you have to prove that. So you have to prove this result. So this is what you want to prove it basically. So you want to prove that there is a, if you start with a point here, you want to prove that the entire neighborhood belongs to omega m. So what is given? You are given that u is subharmonic. So u is given u is subharmonic. That implies Laplacian of u is greater than or equal to 0, but then this also implies this also implies, since m is constant, u minus m is also subharmonic, right? Because m is constant, it is also subharmonic because m is a constant. Okay, so you prove, you can apply mean value property. Now mean value inequality or mean value property, you apply mean value property to u minus the m. M is constant, so you get at the point z u z minus m, because m is a constant minus m. This will be, I can integrate for any ball. Okay, so in particular I can a radius r. So I have 1 by omega n, any r power n, integral over BR of x. This is true because it is subharmonic everywhere. So you have your, in a ball, u of y dy, not u of y, you are applying these to u minus m. So I will have integral over u of u minus m dy. Okay. So this is the result, we get it immediately by mean value theorem. So what do you get it? Integral of, so but what is u minus m? M is the maximum thing. So you have to conclude something from this inequality. Okay, m is a maximum. We have u minus m is always negative. Okay, so u minus m here is negative. So this is less than or equal to 0. So you have both ways 0. So that means this implies integral of, this is a positive quantity. So this is greater than or equal to 0. Yeah, sorry, here we have to write because it is only subharmonic. So you have to write inequality. So 0 less than or equal to this, because it is a not harmonic function, it is a subharmonic function. So otherwise it is fine. So you have this one equal to 0. So that implies u minus m dy over ball of radius r equal to 0. So from how do you prove this integral is negative? So that is a one more step. Okay, so you have an integral. So here you use a result. So maybe if you are not familiar, prove this. Small simple exercise. Simple exercise. Simple exercise tells you that if f preserves a sign, say f is greater than or equal to 0 and integral of f equal to 0 on a domain omega, in omega, these two will imply f identically 0. So assume f is continuous. Okay. So that implies f is identically 0. That is all we are showing. So, we have integral of similarly for negative u minus m dy over br of x is less than or equal to 0 and u minus m less than or equal to 0 for all y, okay, u of y minus m. So, that implies your u of y minus m equal to 0 for all y in br of x. So, that implies br of x contained in omega m. That is so what we want to prove it, right. This is what you want to prove it, br of z. So, you apply it for this z. Okay. So, let me correctly write it. So, this is for z. So, you taken that point z. So, this is for the point z. So, you are take instead of x you are taken this point. So, z. So, does not matter, you can take x instead of z. So, you have proved. So, that implies, so that proves the theorem. Theorem proved. Okay. So, what we will do, we will make some more, this is a strong maximum principle, and with this strong maximum principle we stop for the time being this class, and then from here we can derive some what is called a weak maximum principle, and then I will make some more comments, and then we will prove the uniqueness of our boundary value problem. Okay. Not existence. Existence you may not see except in special cases. The general existence theory will not be covered in this lecture, in this course, because that needs little more terminologies and more time. So, what we immediately prove is the, so you see the mean value theorem, maximum principles, these are all properties we are derived assuming that there is a solution, nice solutions we are derived, and from there we conclude the uniqueness of the theorem. Thank you.